Purchasing a state-of-the-art language model today is like buying an isolated engine. It's incredibly powerful, but completely detached from the gears of your actual business. This diagram maps out a recent study from MIT that analyzed 300 separate enterprise AI projects implemented across various corporate environments. The data revealed a stark reality. 95% of those AI initiatives produced zero measurable impact on the company's bottom lines. In these 300 instances, the underlying models met the technical requirements for reasoning and accuracy during initial testing. The researchers found that the models themselves were capable of performing the tasks they were assigned. The failure occurred when the AI attempted to interface with the customer's actual infrastructure. The models hit a wall of legacy data pipelines and internal security protocols that they were never designed to navigate. A highly capable off-the-shelf model provides no value if it cannot natively communicate with the specific data structures and daily workflows your employees use. Real corporate infrastructure is chaotic. It relies on secure, air-gapped networks, undocumented pipelines held by custom scripts, and highly siloed internal tools. An off-the-shelf LLM exists in a vacuum. Out of the box, it lacks the mechanisms to securely navigate these proprietary environments. The organizations succeeding with AI are the ones willing to do the unglamorous, manual work of hard-coding the connections at the implementation layer. Solving this integration gap relies on two things: a new architectural standard known as the Model Context Protocol, and a highly specialized hybrid developer known as the Forward Deployed Engineer. We are going to deconstruct how MCPs securely wire isolated language models directly into legacy environments, turning a passive chat interface into an active, embedded agent. Building a proof-of-concept AI demo on a laptop is clean, fast work. But taking that demo and integrating it into production accounts for 80% of the total engineering effort. This donut chart breaks down the actual day-to-day workload of a forward-deployed engineer tasked with building an enterprise system. It requires about 25% writing new code, 25% customer communication, and 50% pure integration and plumbing. The coding foundation remains highly technical, relying primarily on Python and TypeScript to script the core agentic logic and build out functional user dashboards. But the bulk of the job is managing the plumbing workload. This means navigating extreme ambiguity, wiring into undocumented legacy APIs, and repairing broken data pipelines on the fly. This cannot be done remotely. A forward-deployed engineer often travels to sit on site, physically writing production code directly inside the customer's secure architecture. The primary bottleneck in AI deployment is strictly an infrastructure and integration problem. To solve it at scale, engineers needed a standardized way to connect models to local data, which led to the creation of the Model Context Protocol. Historically, integrating an AI meant writing and maintaining a custom, bespoke API script for every single application an enterprise used. If an API updated, the entire connection broke. This system architecture diagram illustrates the solution. On the left is your core LLM engine. On the right is the messy cluster of daily enterprise applications. The Model Context Protocol, or MCP, is an open standard designed to replace those fragile custom scripts. The MCP acts as a universal translation layer. It provides a single, unified conduit between the AI model and any local or remote resource. To see this in practice, consider connecting Anthropic's Claude model to a workspace tool like Akiflow.
The complex app cluster simplifies down to a single target, the user's schedule and calendar state. Through the MCP layer, the LLM can pull live context, reading the user's real-time schedule. Critically, it does this without absorbing that raw proprietary data into the model's permanent training set. When it comes to taking action, the protocol exposes predefined capabilities, like create event, to the model as standardized JSON payloads. This creates a strict security boundary. The AI does not receive unrestricted access to the user's system or internal network. The protocol physically limits the model, so it can only see the specific time blocks and execute the exact tool logic that the engineer configured. The LLM processes that tightly scoped contextual data to synthesize a decision, using agentic logic to map a user's natural language request directly to an available action.
By establishing this secure translation layer, the MCP enables an isolated text predictor to function as a context-aware agent within enterprise walls. Wiring the MCP connection is only the first technical hurdle. The integrated system still has to survive contact with live employees. Before it touches production data, the system requires strict evaluation protocols, known as evals. The engineer must quantitatively measure if the agentic loops consistently produce accurate outputs under stress. Once the outputs are mathematically validated, the entire architecture must be containerized to ensure it runs identically across different enterprise servers. The final deployment phase requires deep cloud infrastructure expertise, relying on platforms like GCP and AWS, alongside orchestration tools like Docker and Kubernetes. This complete full-stack requirement, from writing agentic logic to managing cloud deployment, is why these integrations require highly technical software engineers, rather than standard IT support. This circular workflow visualizes the standard deployment loop executed by elite engineering units at companies like Palantir and OpenAI. It moves through 4 distinct stages: scope, build, deploy, and prove. It starts with the scope phase. The engineer sits directly on the factory floor or inside the client's office, decomposing vague customer requests into highly specific, solvable technical bottlenecks. Next, they move through the build and deploy phases, where they wire the MCP integrations, establish the security boundaries, and containerize the agent for the live environment. But the cycle does not end there. This line graph illustrates the final and most critical phase, prove. This role requires a mindset of radical ownership. A forward-deployed engineer does not simply push code, close a Jira ticket, or hand the client a slide deck of recommendations. They remain embedded with the customer until the deployed AI system hits a measurable business outcome, like a proven lift in revenue or a sustained reduction in emergency room wait times. The ultimate value of an AI deployment is never the underlying code. The value is the validated impact on the business's bottom line. The enterprise sector is shifting away from chatting with isolated models and moving toward embedding active, tool-using agents directly into legacy infrastructure. Succeeding in this space requires mastering the complete integration stack, writing core Python, configuring agentic frameworks, and deploying standard protocols like MCP. The most significant economic leverage in technology is no longer found in incremental improvements to foundational model weights. The ability to navigate messy, real-world complexity and deliver a functioning AI system into production is now the most valuable technical skill in the industry.